Today we are going to talk about a new device called operational amplifier. And the reason to develop an operational amplifier is that transistor amplifier usually is quite unpredictable. For example, as we have learned for a common emitter amplifier, right? For a common emitter amplifier, something like this. And this is RC, this is RE. And in the last few weeks, we say the amplification ratio of this amplifier will be equal to minus RC over RE, right? But if you run the simulator, you will find actually the real amplification factor will be, the absolute value will be less than the RAC, and there are quite a few reasons, but some of the reason is that the characteristic of the transistor actually is quite varying, and it also depends on where you bias the transistor. And the other more dramatic amplifier is the common base amplifier. For example, this is the common base of amplifier. This is RC, this is RE, and we have something like this one, right? And there's a PNP amplifier, sorry. There's a PNP amplifier here. And if this is the input, and this is the output, and usually the amplification ratio will be equal to RC over RE. But actually, the real will be greater than RC over RE. Wow, because what? We have a very small RE here. Okay, so it's quite difficult that or even it's not difficult to have a good control of your amplification factor, but it is still will take you lots of trouble such that you can fix your amplification ratio by using the transistor. Okay. So that's why we need the other device such that we don't depend on the characteristic of the device and try to use the parts other than the active device. When we call the active device, we call something like an amplifier thing. For the transistor, you can amplify thing. Of course, operational amplifier, you can amplify the signal. These are called active devices. And the passive device, we call passive device, is something like a resistor or capacitor. This device do not have the ability to amplify things, but it is easy to manufacture such passive device that are and those value of those passive device are usually more accurate and more stable than the active device. But operational amplifier is something very different because it deals on some special characteristic of the operational amplifier, such that the basic characteristic of the operational amplifier cannot affect the amplification factors. That's why we need it. And this is the equivalent model of operational amplifier. So we call it equivalent model. We usually refer it to something that we can turn a circuit into some other circuit, some simpler circuit, so that we can solve. And basically the equivalent model, so that we can solve the circuit by using the KCL and KVL, or such very simple circuit analysis tools. And for the operation amplifier, we have the input model. The input model and the output model actually are separate. The input model is only a resistor, and usually we will ask the resistor, the R in is very, very big, and these are the input voltage that is seen at this terminal, and this one will be amplified by the gain, this is G, and we want G to be goes to infinity, or at least 500, something like that. And we also want it to have the output impedance. This will call this one the output impedance, and we also want the output impedance to close to 0. Okay, this is the amplifier. And usual operational amplifier has lots of different kind of packages, but this is typical. We call this one package the DIP type of the package. So it has at least a 2 terminal. The first terminal we called it the non-negative input, and this part is negative input. Okay, so we have V plus. We have the V plus and the V minus, and we have the power supply, which positive and negative power supply, and we have the output here. So usually we only use 5 pins of that, and sometimes 8-pin DIP package operation if I can have 2 amplifier in a very small one. Okay, and there are 2 very small pin here. The off node here is that if Vs plus N is not equal to Vs minus, okay, it turned out that when input is 0, but the output is not equal to 0. So this 2 pin is to adjust that, such that if there is no input signal, we have 0 output of the amplifier. So we call this is the equivalent model of the operation amplifier. Why operation amplifier has such kind of characteristic that the amplification factor can be determined by the external passive parts, is that first one. Okay, we will see why, but let me first state the characteristic of the idea operational amplifier. The first one is that it has an infinite open loop gain, means the G has to go to infinity. The second one is that, which is also important, is that it has infinite input impedance, mean R in goes to infinity. This also means that you will have a 0 input current. Okay, imagine that this is a very good characteristic, because that if R in is infinity, then if I have a signal Vs, the Vs has its own output impedance called the RO. If I connect to the OP, operation amplifier, and this one is the R in, then the signal here, the input signal Vi here, the Vi will be equal to R in over R0 plus R in, and multiplied by the Vs. And we can see if R in goes to infinity, then the VI will be very, very close to VS. So we don't waste the signal VS. Okay, so and of course this is very important. This is the zero input offset voltage. I just explained if you don't have if the input VS is equal to 0, we want VI is equal to 0, also 0. And the third one is input infinite output voltage range. Of course, it's not possible because we have the limited the power supply voltage. This is impossible, but it's this idea. We have infinite bandwidth, zero phase shift, and an infinite slew rate. Okay, what is phase shift? Phase shift refers to something like this. So if for example, if the input is this is the output. If input is sine omega t, and the output is sine omega t plus phi. Okay, and this is some amplification circuit. And phi is called the phase, right? Okay, if phi is a phase, what does it mean? Okay, first we can try to rewrite the sine function by taking out the t, will be t plus if I put a minus phi here, would that make it easier? Sorry. Okay. And we will find that this is a sine omega t, right? This is the input. But what about the output? For example, if phi is equal to 1 over 4 pi, okay. So for example, if I have the frequency f equal to 100 hertz, okay, then what about omega? Omega will be equal to 2 pi multiplied by the f, which is 200 pi. So if the phase is a quarter pi and this one is 200 pi, then we will 1 over 800 seconds. That means that the sine wave will be delayed by 1 over 800 seconds, right? And we call this one the phase shift. Okay, means that the input signal is altered, and what is altered? Because the signal is delayed. Okay, we don't want this, so the zero phase delay, we want the phi equal to 0. Okay. And what is the infinite slew rate? Infinite slew rate means that what is infinite slew rate? Infinite slew rate means that if I have a signal, okay, I have a signal, the signal goes from 0 to 1 at time t equal to time 1, okay? And what is the slew rate? Slew rate means that the amplifier can follow the signal. How fast can follow signal? Okay, so it is something like this one. So this one, we have this kind of type. Okay, we also can have second type. So this one we call it a higher slew rate because it follow the input signal faster, and this one has a lower slew rate. Of course, we usually want is a higher slew rate as high, the slew rate as high as possible. So this is we want infinite slew rate. Okay, so next, go to the next one. The next one is that we want to have the zero output impedance. Why zero output impedance is important? Because our output is something like a power source and connected to an output impedance. And we are going to have another circuit which will have input impedance connect here. We have V here. So this is the V out, and this is the V in. So V in will be equal to V out, and Ri, R0, Ri, R0 plus Ri. So if R0 goes to 0, then V in will be equal to V out. That's why we want it has a zero output impedance. Of course, zero noise. Okay. The next term to explain is called the common mode rejection ratio. The common mode rejection ratio means that we have an operational amplifier. This is non-negative input, this is negative input. So we have a V plus and a V minus. But in case we have a noise goes inside N of T here. Okay. So at this point is V plus N of T. V plus T of N of T. At this point we have V minus T plus N of T. And we want the V out of T here. There will be something plus A and rho T. And this term is purely from noise. And we want this A is as small as possible. So if this one is very small, we call it has an infinite common mode rejection ratio if A equal to 0. Okay. The last one is the power supply rejection ratio. Power supply rejection ratio means that if we have the noise from the power, we have power with VS1, V plus VS minus. We also want the noise term, the A noise term, we also want this one to be 0. So this power supply rejection ratio, which is quite important to amplify. Okay, this is the ideal operation amplifier. So, okay, this I already explained this term about the offset voltage, the bandwidth, the phase shift, the slew rate, and the common mode rejection ratio, and the power rejection ratio. So you can Google and read more detail of this definition. Okay, they are important, but won't be part of the examinations. So let's look at the typical operational amplifier. They're very small and very cheap one called 741. So as you can see, the offset voltage is only 1 millivolt, maybe 5 or 6. It's small. And we can adjust the offset voltage in case that we want true 0 offset voltage. We can adjust plus and minus 15 millivolt, which is quite enough to adjust the offset voltage. But be sure that your power supply Vs plus and the Vs minus should be as close as possible. Okay, so we have the current, meaning when it's idle, okay, the current is very small. This is only narrow ampere, meaning that it saves the power. And the input impedance is 2 mega ohm. Okay, this is usually quite large in most of the applications. And we have input voltage range plus and minus 13 volts. Okay, and we have voltage gain, not very big, 200. And output voltage swing can be as large as plus and minus 14 volts if you give the 15 volts as your power supply. Okay, and the common mode rejection ratio was 95 dB, and the power supply rejection ratio is 96 dB, also quite big. Through rate is not very impressive, only 0.6 microsecond. Okay, it's not very big. Through rate is not very good, but still acceptable. Okay, the power consumption is very small, only 60 milliwatts. Okay, but if we go for a better operational amplifier called 5532, it's usually used in audio application. That's an AV receiver. Okay, you can use in DVD recorder and the player. You can use it in the pro audio mixer. Okay, so this is the basically it's spec. Okay, and as we can see, its offset voltage is even smaller. It's only 0.5 millivolts. Okay, the operational current, the bias current is still very small in narrow ampere level, and the input voltage range is quite similar. Okay, plus minus 13 volts. Okay, and the amplification gain is not very big compared to the 740 or the 100 here. Okay, and the output impedance is 0.03 ohm. Okay, it's very high bandwidth, 10 megahertz. Okay, and the common mode rejection ratio and power supply rejection ratio is quite impressive. So over 100 dB. Okay, and basically, operational amplifier is also made by a transistor, and this is the 741 internal structure, but that's a simplified one, and it has the following few amplification stage. First is that we call it a differential amplifier, which may be covered in this semester, in the last stage of this semester. This is a differential amplifier. Okay. The second one is the red box called the current mirror, which is quite important. Okay, and quite useful design that is used in electronic circuit. This is a current mirror or the current supply. We'll talk about it later. This is also the current supply. And then we have the gain stage. Okay, this is the gain stage here. Gain stage here is very similar to a common base or common emitter amplifier, and we will have a level shifter. This level shifter is used to shift the signal level and also maintain the bias of the output stage. And finally, the output stage is we call the push-pull output stage. Okay, this is push-pull output stage. This circuit will be introduced in the following parts of the lectures. okay, all are very useful and important and basic. So the material of this semester actually generally follow that this one, except that we will have the MOSFET introduced first, and later we'll introduce this circuit one by one. And why the operational amplifier has this kind of characteristic that the amplification factor can be solely defined by its peripheral passive elements. Okay, for example, this one. Okay, we use this one as an example. And this is the operational amplifier, and this we call an inverting amplifier, meaning that the input comes in from the inverting part. And because we have very high input impedance, this one goes to infinity. So the current flows through here. The current, the I here, will be close to 0. So that means that the current flows through here and the current flows through here. Okay, the sum should be the same. So we can write the equation like this. We have V in over R in plus V out over RF will be equal to 0 because I equal to 0. This one I is equal to 0. Okay, so let's do it. So V out over RF will be equal to V in minus R in. So V out over V in will be minus RF over RI. This goes here. Okay, meaning that the input signal is amplified by a factor of RF over R in, but inverted. Okay, very simple. We have the negative feedback here. So usually we call this one a negative feedback amplifier. Okay, why is it negative? We'll talk about it later. Okay. And this one also is a negative feedback. Okay. As you can see, this one is positive, right? And this one comes in as negative. And this one goes here, so the sign of the output signal and the input signal are different. So we call this the negative feedback. Okay. And what about if the input comes in from the positive side? So we call this as a non-inverting amplifier. This is a non-inverting amplifier. Okay, and because this one goes to infinity, so the voltage here and the voltage here will be approximately the same. Okay, so V out, okay, multiplied by the R1 and R1 over R2, R1 over R1 plus R2 will be equal to V in. So if I rewrite the equation, this one will be equal to R1 plus R2 over R1, which will be equal to 1 plus R2 over R1. Okay, this is the amplification factors. So as you can see, the amplification factor is purely decided by the peripheral passive elements. And this one is also negative feedback because you see here we have the plus here, but we feedback here to the negative side. This is the negative side, okay? This is the negative side. So we call it a negative feedback. So the feedback system diagram of a non-inverting amplifier can be represented by this very simple graph. And this very simple graph actually is applied to many application and area. So in general, if you want to have a system to be more stable, you usually will apply negative feedback technologies. Okay. And usually if I write, I draw a diagram, something like this, I have an input here, this one with plus, and the open loop gain usually is a plus, is a positive one, and I will have a negative one, and the operation here means that the R minus H, okay, here, because H comes here, okay. And let me show you how to find the ratio between the output C and the input R. Okay. As you can see, the E part will be equal to what? Will be equal to R minus H, right? Minus here. But what about H? H actually is H multiplied by the C. So E will be R minus H multiplied by the C, right? But what about C? C, well, actually is the E multiplied by the G, right? So let's replace E by R minus H of C. So C will be equal to R minus H plus C, okay, times G, right? Okay, this C is the output, R will be the input. Okay, so C will be G multiplied by R minus H, G multiplied by H multiplied by the C. Okay, so let's move around. So 1 plus G multiplied by the H multiplied by the C will be equal to G multiplied by the R. Okay, so finally we have R, C over R will be equal to G 1 plus GH. Okay. So this is the input. No. This is R is the input. Sorry. So R is the input. C is the output. Okay. So as you can see, we can easily calculate the amplification factor of the amplifier. Okay. So let me erase this. So because for operational amplifier, G is almost infinity. So C over R will be equal to what? G plus GH. But since G is very big, okay, so let's assume one is very small. So G is eliminated. So the amplification vector is usually 1 over h, right? So then what is the amplification feedback factor? So in the non-inverting amplifier, let's look at it. In non-inverting amplifier, the feedback ratio is R2 over R1 plus R2. In non-inverting, configuration, the H, well, actually is R1 over R1 plus R2. So that's why, okay, when you make a reciprocal, you will have the R1 plus R2 over R1. Okay, that's why is that is amplification factors. So it's very easy to use. So for inverting amplifier, we can do it in a similar way. This is inverting amplifier. Okay, we can do it amplifier, and this one goes to infinity, right? 2 goes to infinity. I will let you do it yourself. And how much is H1? How much is H2?